The paper of the day is a critic of ANSI SQL isolation levels. The ANSI SQL isolation levels were originally defined in rows in terms of three specific anomalies that they were designed to prevent. And surprisingly, it turns out that those original definitions are somewhat ambiguous and open to both a strict and a broad interpretation. It also turns out that they are not sufficient, since there is one even more basic anomaly not mentioned in the standard that needs to be prevented in order to be able to implement rollback and recovery. Looking even more deeply, the paper uncovers 8 different phenomena that can occur in 6 different isolation levels. So here is the pictorial representation of the different isolation levels. It goes from degree 0, where anything can happen. Then we forbid dirty writes in P0, and then graduate to read uncommitted, which is degree 1. And then again, if we put a restriction of forbidding dirty reads, then it leads to read committed, that is degree 2. If we forbid cursor lost updates, then it leads to cursor stability. And if we now forbid fuzzy non-repeatable reads, it is P2, it leads to repeatable read. And now if we forbid phantoms, it leads to serializable. And then we have arrows from read committed to wrapper consistent reads, which is incompatible with cursor stability. Then we have right hand arrow where we forbid lost updates, that is P4, forbid read skew, we don't allow phantoms, A3, then that leads to snapshot isolation, and we forbid write skew, and that leads to serializable. It's a bit complicated. Isolation levels. So let's talk more about it. So a transaction has well-formed writes and reads if it requests a write or read log on each data item or predicate before writing or reading that data item, or set of data items defined by predicate. The transaction is well-formed if it has a well-formed writes and reads. A transaction has two-phase writes or reads if it does not set a new read or write log on a data item after releasing a read or write log. A transaction exhibits two-phase locking if it does not request any new logs after releasing the sum log. One reason why dirty writes are bad is that they can violate database consistency. However, the constraint can easily be violated if the two transactions write x and y in different orders, which can only happen if there are dirty writes. So in this picture, T1 writes x equal to 1, then T2 writes x equal to 2, and then writes y equal to 2 and commits. And after that, T1 writes y equal to 1, and commit, and there's an inconsistency. A dirty write occurs when one transaction overwrites a value that was previously being written by another still in flight transaction. Another pressing reason to protect against dirty writes is that without protection from the system can't automatically roll back to a before image on a transaction abort. That is, even the weakest locking systems hold long duration write locks. Well-formed writes and long duration write locks prevent dirty writes. Other than the serializable level, ANSI SQL isolation levels do not exclude dirty writes. However, ANSI SQL should be modified to require P0 protection for all isolation levels. So dirty read. A dirty read can occur when one transaction reads a value that has been written by another still in flight transaction. So in the figure, the intent is to transfer $40 from x to y, and the constraint is x plus y should be equal to 100. So x equal to 50 is read, then the value is subtracted, so x becomes 10 and it's written, and the y value is 50. Then if T2 reads x, it reads as 10. Now at this in this window, x plus y is equal to 60, which is inconsistent, and it remains inconsistent till y writes till the $40 is transferred to y and y becomes 90. At that point, the constraint of x plus y equal to 100 is maintained. So in a locking based implementation, well-formed reads and writes combined with holding short duration read logs and long duration write logs will prevent dirty reads. P3, phantom. A phantom occurs when a transaction does a predicate based read, that is select where P, and another transaction writes a data item matched by that predicate while the first transaction is still in flight. In the original ANSI SQL language, only matching inserts were forbidden, new entries being phantoms. But in fact, to be safe, we need to prohibit any writes, update, deletes, inserts. In a blocking-based implementation, well-formed reads and writes coupled with a long-duration read locks, both data item and predicate, and long-duration write locks will prevent phantoms. So here is the image. So in this figure, you have active employees and you have active employee count. So T1 reads and gets the active employee count as CTH. Then T2 inserts M. So the active employee count becomes 4 and it commits. And when T1 reads again, it sees as 4, which is it. And there's a window where it's kind of there's a discrepancy where T1 is actually sees 3. It assumes 3, but actually it is 4. Last update. It turns out that there is an anomaly that is not prevented by systems that defend against dirty reads and dirty writes, but that is prevented by systems that also protect against fuzzy reads, is known as the last update. Consider the following history. There is no dirty write since T2 commits before T1 writes X. There is no dirty read since there is no read after the write. Nevertheless, at the end of this sequence, T2's update will be lost even if T2 commits. So let's go through the image in detail. So here T1 reads X equal to 100, then T2 reads X equal to 100, and then T2 writes X equal to 120 and commits. And then T1 writes X equal to 130. Now all the updates from T2 are lost. So this is the last update. Cursor lost update. P4C is a variation of the last update phenomenon that involves a SQL cursor. So in this history, we have T1 reading 100, it's a read cursor, T2 writes X equal to 75, and then T1 writes X equal to 110, and we have lost the value written by T2, that was X equal to 75. So in this history, let R6 represent a read of the data item X under cursor and WCX a write of the data item X under the cursor. If we allowed another transaction T2 to write to X in between the read cursor and the write cursor actions of T1, then its update will be lost. In a locking implementation over the requirements to prevent P0 and P1, holding a lock on the current item of the cursor until the cursor moves or is closed will prevent cursor lost updates. Write skew. So let's see the read skew. So here X reads X equal to 50, T2 writes X equal to 25, and then writes Y equal to 75 and commits. And then T1 reads Y equal to 75, and then it commits or aborts. So here, read skew can occur when there are integrity constraints between two or more data items. Consider the constraint X equal to Y equal to 100 and the history shown in the figure. When T1 reads Y, it sees an inconsistent or skewed state and may therefore generate an inconsistent state as output. Write skew. Write skew is very similar. Suppose our constraint is X plus Y is less than or equal to 100, and this time we interpose a transaction before T1 issues a write. So here T1 reads X equal to 30, T2 reads X equal to Y equal to 10, then T1 writes Y equal to 60, and then T2 writes X equal to 50 and commits. So here again the constraint is kind of violated. And there's an inconsistent there's a data inconsistency, and X plus Y less than or equal to 100 constraint is not maintained. All right, so next slides, isolation level summary table. So here, so this graph captures all the different isolation levels and what is allowed and what is not allowed. So we have read uncommitted, read committed, cursor stability, repeatable read, snapshot, and serializable. There are two other isolation levels discussed in the paper: Oracle consistent read and snapshot isolation. Like cursor stability, the read committed is less than the Oracle consistent read. Read consistency isolation gives each SQL statement the most recent committed database value at the time of the statement. It is as if the start timestamp of the transaction is advanced at each SQL statement. The members of the cursor set are as of the time of the open cursor. The underlying mechanism recomputes the appropriate version of the row as the statement timestamp. Row inserts, update, and deletes are covered by the write logs to give a first writer wins rather than a first committer wins policy. So let's talk a bit about snapshot isolation level. Each transaction reads data from a snapshot of the committed data as of the time the transaction started, called its start timestamp. This time may be any time before the transaction's first read. A transaction running in snapshot isolation is never blocked attempting to read as long as the snapshot data from its start timestamp can be maintained. The transaction writes, that is, update, inserts, and deletes, will also be reflected in this snapshot to be read again if the transaction accesses, reads, or updates the data a second time. Updates by other transactions active after the transaction start timestamps are invisible to the transaction. Both snapshot isolation and Oracle consistent reads are types of multi-version concurrency control mechanisms in which we have to reason about multiple different values of the same data item at any given point in time. It turns out that all isolation level histories can be mapped to a single valued history while preserving data dependencies. So we have read committed, which is, and then the greater isolation level is snapshot isolation level, and then again greater than that is serializable. But snapshot isolation and repeatable reads are incomparable. Snapshot isolation permits write skew, which repeatable read does not, and repeatable read permits some phantoms which are not permitted under snapshot isolation. Pretty cool.